Hello and welcome. This video is going to explain normalization as it relates to relational databases. Okay, so it will go through a complete example of to produce a normalized database, but at the beginning I'm going to cover off terminology so that we understand what the primary keys, foreign keys, bridge tables, relationship types, etc. are. Because if you don't understand that, it's very hard to understand the database themselves. So if you know all that stuff, you can skip right to the example of the normalization later in the video. Okay, so we're going to cover first normal form, second normal form, and third normal form. There are other normal forms, you know, BCNF, fourth, fifth, even a sixth normal form. That's more in academic discussion papers, but not really seen. You can stop at third normal form probably for over 99% of database designs. It's just fine. So we're just going to cover third normal form. Okay, so let's get started. And first I'm going to just cover off some basic stuff. Okay, so first thing I want to talk about is what is a table. This is a representation of a table. We use tables to store our data. It's just a two-dimensional representation of columns and rows. So every column will have in every table, the columns will be unique, and the columns, you'll just make up the names of the columns that describe the type of data that's going to be in the column. So here, the name of this column is product number. So obviously in this column, I'm going to store product numbers, and product name column is going to store the names of the products, etc., etc. So make them make sense. Every table will have a name. Okay. Now these columns are known by the names column. Some people will call them fields. Some people will even call them attributes. The rows, also known as records or even tuples, okay, but I'll change the words. Sometimes I call them rows, sometimes I call them records. For the columns, sometimes I call them columns, and sometimes I call them fields. Okay, these are the values. Okay, the intersection of a row and column is a value. So what's the value for the product name in this row? It's apples. Okay, so these are the values. Okay, every column name in a table must be unique. So you can't have two columns with the same name. In different tables, that's perfectly fine. Okay, no problem there. But in the same table, you cannot. Okay, let's continue. Now, here I'm showing two tables, and they're related to each other here through this link. This is why they're called relational databases, because all the tables are related to each other in some manner. Now, what I want to point out here is this column here in this table, the product ID column, and in the category table, we have a column called category ID. Notice I've underlined the column names. That indicates a primary key. Okay. Every table that you create will have a primary key, okay? And a primary key has three characteristics, okay? And they are, the values must be unique. So all these values, no matter how many rows you have to be unique. In other words, they cannot repeat, okay? I can never have another row in the product table that has a product ID of 2, because I've already used it, okay? So it has to be unique. The other characteristics is it cannot contain a null value. Null means no value whatsoever. So in other words, it's saying you must have a value in here. You can't leave it blank, okay? Any column that's part of the primary key must have a value, okay? Can never leave them blank. And the third characteristic of a primary key that most people don't talk about is it must be the minimum number of columns to create uniqueness. Okay. In this case, I have a single column, but you're going to see later that when we do the normalization, that is very important, this last one, or else you actually end up with an improper design. Okay. In this case, I have one column that I can use as uniqueness. you'll notice that this column here, product number, if every product has a unique product number, this column could have been used as a primary key. This is known as a candidate key. Okay, so other columns could be a primary key, but you just pick one or two. One column or two columns to make up the primary key. You'll see that later. But you pick something to make the primary key. Okay. If there's another column or combination of columns that creates uniqueness, those are candidate keys. Okay. This column here, category ID in the product table, is known as a foreign key. A foreign key is the column that links a table to another table. And usually it's from a primary key of one table. So the category, the primary key is the category ID, links to a foreign key in another table. Notice mine are the same name. They don't have to be. I'll talk about that later when I do the naming conventions. Okay. So a foreign key is used to link the tables together. Okay. You'll notice a foreign key values can repeat. That's no problem. Let's see how this works, what this means. You can see here this product, which is apples, has a category ID of 1. What does that mean? What category does apples fall into? Well, you look here for a 1. You go down through the link. This is the column it's linked to, so therefore you find the value of 1, which is here. Then you look here to the category name and you see that it's a category of fruit. Okay, this one here, chicken, is a 3, so you go down here, you find the 3 here. It's the category of poultry. And here's a 1 again, which is fruit. And this one here, sugar, is a 4. You go down here, that's a baking category. Okay, that product falls into the baking category. Okay, what you'll notice when you finalize your design, that every table contains, it's basically a noun, so it's a person, place, thing, or event. Okay, you'll find. So this is a thing, it's a product. This is a thing, a category. Okay, so you'll see that later. I'll explain that in more detail later. But a foreign key links the tables together. Okay, these values in the category, in the foreign key, must exist in this table, the linking table. That's known as referential integrity. I can't put a product in here in this table, and I couldn't put a category ID of 5 here because it wouldn't make any sense. There's no category called with a number 5. So these values have to exist in this table. Okay? Now, what I'm showing here is this table has a single column as a primary key. This table called product has a single column as a primary key. Notice this table has 2 columns underlined. When you have 2 or more columns making up a primary key, it's called a composite primary key. The table still only contains 1 primary key, but it's made up of 2 or more columns. In this case, 2 columns. Okay, so it's called a composite primary key. Now the same rules that we had for the primary key still have to be in effect. In other words, we have uniqueness. And now what do I mean by uniqueness when it comes to a composite primary key? You'll notice here the invoice ID repeats, and you can see even the product ID repeats, but the combination of the 2 never repeat. So when you look at a composite primary key, you have to look at all the values in all the columns that make up the primary key for uniqueness. It's the combination. So in this case, a 1 and 1 can never repeat ever again. A 1 and 4 can never repeat again. No matter how many rows I put in, that combination can never repeat ever again. Let's see how this works. This line, basically this is what you'll see later called a bridge table. I'll explain that later. But let's analyze it for a second. This invoice, which is 1, you go up here, find a 1. That's the invoice number. That was the date of the invoice. and there's a column called customer ID. It's a 5. Well, that's a foreign key to another table called customer, which I'm not showing, okay? But through here, I could see the invoice number, the date of the invoice, and the customer who purchased these products. What products did they buy on this invoice? Notice there's 2 invoice IDs the same, which means there's 2 line items on this one invoice. One product they bought, which is a 1, which is apples, and they also bought a 4, which is sugar. So they bought apples and sugar on this one invoice. This one here has 3 items on the same invoice. A product 1, a product 2, and a product 3, which is apples, chicken, and oranges. Okay, and you can see how many they bought of each product, the cost to the store, say, and what they sold it for. Okay, so this is a composite primary key. All right, a composite primary key, again, is a primary key that's made up of 2 or more columns. It's still considered one primary key, and you have to look at the combination of all the values to get uniqueness. Okay, so composite primary key. Now, when you're designing, you have to figure out business rules, and business rules are just simply some kind of description of the policies or what the customer wants, okay, within an organization or whatever the customer does. Okay, so business rules, once you figure out the business rules, they will help you define your entities, which are another name for tables. Okay, that's, I forgot to say earlier, but tables, some people call them entities. Some people will call tables relations. Okay, it also tells you what your columns or fields are, your relationship types, and your constraints. I'll explain these later. The main source of your business rules is from your client, from your end users. You talk to people and see what they want. You also look at any reports they have existing. So for instance, if you're asked to create an invoicing program and they already print invoices, get a copy of their actual printed invoice, because everything that's on that invoice has to be in your database, or else you can't regenerate the exact type of invoice, right? If they have ship to addresses on their invoice, you know you need a table to accommodate ship to addresses. You need, say it's delivery methods, you would need a table to handle your delivery methods. Okay, so any reports they have existing, get a copy of those too. You talk to the end users, you talk to the people who are going to use the application to figure out what they need. Okay, now I mentioned earlier relationship types. In a relational database, there's 3 types of relationship types. There's a one-to-one, a one-to-many, and a many-to-many. Okay, I'm going to read off a description or a sample of each one, and then I'm going to show you how they work. A retail company, so a one-to-one is a retail company may require that each of its stores be managed by a single employee. In turn, each store manager who is an employee manages only a single store. The relationship between employee manager store is one-to-one. I will say this, if you end up with a one-to-one, or think you end up with a one-to-one between 2 tables, double check it. They're very rare, okay? The majority are one-to-many and many-to-many. So double check. If you think you end up with a one-to-one, just double check it, okay? Not saying it doesn't exist, just double check it. A one-to-many, an example of this, a painter can paint many paintings, but each painting is painted by a single painter. So the relationship between a painter paints the painting is one-to-many. A many-to-many relationship, a student can take many classes, and each class can have many students in it. So the relationship between a table called student and a table called class is a many-to-many. Now, in a relationship schema database, if you end up with a many-to-many, you have to get rid of the many-to-many. The final design cannot have a many-to-many relationship in it, okay? You break it up into two one-to-manys, which I'm going to show you how to do. Okay, so the final design cannot contain a many-to-many relationship. Here's an example. We have our invoice table and we have our product table. Now, it's very, very, very important you get the relationship type correct when you're designing a database. Okay, if you don't get it correct, it changes the design. Okay, so let me explain how you do it. It's very simple. This is not the normalization process, but this is a way you can do it without the normalization process, also to double check the final normalized design and everything like that. Okay, so we have an invoice table and we product table. What you have to do is make two business rules. Always have to make two business rules. Okay, I call them bi-directional business rules because what you do is you make one rule going from the invoice to the product and one rule going from the product to the invoice. So you go opposite. So let's see what I mean by that. Let's start with going from the invoice to the product. What I want to do is figure out what's the relationship type between these two tables. We know they're related because when you create an invoice, you have products on it, and products appear on invoices. So they're related somehow, but the question is, how are they related? So I'm going to start with the invoice table and go towards the product table. And it's very simple. You just make a sentence. Start with the word one. I usually start with the word each, but I'm going to start with the word one because I told you relationship types are one-to-one, one-to-many, or many-to-many. So you say this: one invoice can have how many products on it? One or more than one. More than one means many, so it's one or many. So each invoice or one invoice can have how many products on it? If you say one invoice can only have one product on it, that means for every invoice I can only sell one thing. That's probably not what you want. One invoice, I can sell many products on the same invoice. So think in the store, in a grocery store, you take a whole basket of food up, different products. That's your receipt that you receive. That's the invoice. Okay. So if you go into a store like Home Depot or something, you go in and you buy a lot of things. Okay, so each invoice that you have has many products. So that probably makes more sense. So one invoice can have many products. Now what you do is you go the opposite way. You start at the product side and go towards the invoice side and make another sentence. And you start with the word one again. So one product can appear on how many invoices? If you say one product can appear on one invoice, that means if I sold apples on this invoice here, I can never sell apples again. I can't have it ever appear on any other invoice. So the chances are what you want is one product can appear on many invoices. You can sell the same product on many different invoices. So now the sentence says one product can appear on many invoices. Then you look here and you see a many on the product side and you see a many on the invoices side. Therefore, the relationship between these two tables is a many on the products and a many on the invoices. So it's a many-to-many relationship. I just told you earlier, the final design cannot have a many-to-many. So what we have to do is get rid of this many-to-many. And it's very, very simple. All we do is put a new table in between these two tables. We call that a bridge table. Some people call it a joining or linking table. So we just put a bridge table in between. And the minimum number of columns that are in this table is the primary key from this table and the primary key from this table. So there they are, invoice ID and product ID. That's the minimum number of columns that must be in it. The two together usually become the primary key of the bridge table. Sometimes you can add a new column, like date is a common one, and the three would be a composite primary key. But right now this works just fine as the invoice ID and the product ID combined become the primary key. Okay, that's the minimum. I could add others to accommodate whatever I need it to do. Individually, they're foreign keys. Okay. Now, you see I wrote the relationship type between them. A 1 on this side and a many on this side. The infinity sign means many. 1 on this side and many on this side. Why do I know that? Always remember, wherever the foreign key is, that's the many side. So invoice ID is the primary key on this side. So that's the 1 side. This is the foreign key. By itself, it's a foreign key, so it's the many side. Combined, they're a primary key, but individually, they're foreign keys. So the many side always goes on the foreign key side, okay? So that's a bridge table. That's how you get rid of a many to many, okay? Now I can accommodate this rule. Each invoice can have many products. Look, this invoice has 2 products. This invoice has 3 products. Each product can appear on many invoices. Look, this product 1, which is apples, has appeared on 2 different invoices. This invoice and this invoice. So I've accommodated both of these conditions using a bridge table. Okay, that's what the bridge table does. And give it a name. I just call it invoice detail. So I call it something detail. Okay. Let's look at naming conventions. Just like any programming language, you should get used to using some kind of naming convention when it comes to designing your databases, okay? So object names, some people, for instance, an object is a table. Some people might prefix the table with, you know, a prefix like TBL to indicate a table. I don't. I'll just call it product, okay? Also, you should, table names should be singular and not plural. Don't add S's to the names of tables. Nothing says you can't, but it's normally not done. People won't put an S, won't pluralize it, okay? Okay, so for object names such as your database name, your table and column names, you don't use reserved words. What are reserved words? They're words that denote some kind of SQL command or function or procedure. So these are words that are used in the SQL. Like you wouldn't name a table select or a column select because select is a key word. It's a statement in SQL. You wouldn't call it maybe date because date is a reserved function. It's a function or procedure that's in most database systems, okay? So you got to be careful. Don't use reserved words. And depending what relational database system you use to design your database, you might use Oracle, you might use MySQL, you might use SQL Server, Postgres, whatever the case may be. They have different procedures and they have different names for the procedure. So are you going to memorize all the stored words? I don't. What I do is to avoid this problem, I prefix all my column names with the name of the table. So if I have a table called invoice and I need a date column called date in that table, I will actually call it invoice date. The invoice is the name of the table and then date is the name of the column. So if I have an employee table and I want their first name and a last name, I don't just make 2 columns, one called first name and last name. I will call it employee first name and employee last name. So I use the name of the table as my prefix, and you'll never run into a problem with reserved words. Okay, it's also not a good idea to use spaces in your object name. So let's say you have a column called student space first space name. Perfectly valid. You won't get an error. The problem is when you're programming or typing in your SQL statement or anything like that, you must remember to enclose that object name or column name in quotation marks like this. Quotation, student space first space name quotation. If you forget to leave it put in quotations, you'll get an error message. So to avoid having to remember that and typing a little extra, you might put underscores. Or do what I do, just shorten it with something like this, student F name. I know that means the student first name. Student L name would be their last name column. Okay? So figure out what you want to use. I just recommend you don't use spaces. It just becomes cumbersome. Only use alphanumeric characters, okay? 0 to 9 or A to Z or Z. You can use other characters, but I would stick to the standard characters, okay? Always start a database, table, or column name, so any of these objects, with a letter and not a number. You're not allowed to start an object name like a table or column with a number. It has to be a letter. You can have a number in the name, but it can't be the first character, okay? So try to remember these naming conventions. Now we're going to get into normalization, what we came here for. Okay, we're going to break it up only into 3 normal forms. First normal form, second normal form, and third normal form. Definition of first normal form. Each column value must be a single value only. In other words, it has to be atomic. Each column and row intersection can only contain a single value. Okay, that's what we mean by atomic. So for instance, if I have a student name, technically you have first and last name. So that's 2 different values, a first and last name. Okay, so you would normally break that up into a first name column and a last name column. You don't have a column, say author. You don't store 2 authors' names in the same row column intersection. You'd have to break that up. Okay, you can't have 2 values in the same column. Now, a date, like say a student's date of birth, that consists of a month, day, year. But when it comes to relational databases, we consider that perfectly valid. That's considered a single value. That is the student's date of birth. Dictionary definition of atomic means non-divisible, and a date technically is divisible. So it's not that type of atomic. It's not the dictionary version of atomic. We do not break it up into month, day, year. We would just keep it as the student's date of birth, okay? And it would contain the month, day, and year in the same row column intersection, okay? So don't mix those up. You have to remove all repeating groups. That's a hard one to explain in words. It's easier to show you, so I'll be showing you that after I explain this stuff. All values in a column must be of the same type. So if they're all student date of birth, they all have to be student date of births. They can't be something else. If they're all company names, they all have to be company names. You can't use like a person's name unless the name of the company is a person's name, okay? So that's what that means. Each column name must be unique in a table. I mentioned that earlier. Column names can repeat in different tables, but not in the same table. No 2 rows in a table can be identical. So that means no duplication. You can't duplicate data in a relational database. Second normal form is you meet all the requirements of first normal form. So all these are true. And you will remove all partial dependencies, okay? So that's all of its non-key attributes are dependent on all of the primary key. So in other words, all of the columns that do not make up the primary key are dependent on the primary key. Again, you'll see that when we do normalization. You'd only get partial dependencies if you have a composite primary key. If you only have a single column as a primary key, you have no partial dependencies. Third normal form, a table must meet all the requirements of the second normal form, and you cannot contain transitive dependencies. So at this stage, you will remove your transitive dependencies. Transitive dependencies say all the non-key columns, meaning all the columns that do not make up the primary key, must be dependent on only the primary key and not any of the other columns. Again, you'll see that. So that's the definitions of normalization, the three normal forms. Okay, here I'm showing you what people consider a repeating group. Okay, if I have a simple table like this that has 2 columns for the author's name and a book title and the category. Okay, you can see this. Suzanne Collins wrote a book called The Hunger Games. Dan Brown wrote Lost Symbols. Dan Brown also wrote the book The Da Vinci Code. But here I have Dorothy Sayers and Robert Eustace wrote The Documents in the Case. And also down here, Malala and Christina wrote I Am Malala. So I have 2 authors writing the same book here, 2 authors writing this book here. The problem with this design is this. Say you gave this to a client and you wrote the application and everything for it, the front end, like the interface for it, and this is the back end, the actual database, storing all the data. Then they came to you and said, oh, you know what? We have a book now that has 3 authors. Well, what do you got to do? Well, you got to add a new column to this table to accommodate the 3rd author, which means you have to redesign your whole database, change your front-end application and everything like that to accommodate the 3rd author in your reports, in your screens, when you're filling in data. A lot of work. And then you fix that, and then they come and say, well, we have 4 authors now on this book. Then you have to redesign everything again, add a new column, ba-do-do. The problem with that is you're designing a table horizontally. You never design the table horizontally. A table should be designed vertically, meaning you just have to add rows or records into the table to accommodate any situation the client has. Okay, you should not have to go back and redesign your database and your application every time the customer wants something new like that. Okay, so this is called a repeating group right here. The other way of looking at that is this. Well, what if I just make 1 column for author, like this? There, I have 1 column for author. And now this book here, the documents in the case, I have 2 authors, right? See there, Dorothy Sayers and Robert Eustace. I separate them with a comma. Maybe I'll use a semicolon. I don't know. I'll use something to separate them. Well, you broke the rule of first normal form, which says every column can only contain 1 value, meaning atomic. You have 2 different values in this column. You have 2 values. So you can't do that either. So you can look at a repeating group this way, with multiple columns, or some people look at it this way. I look at this as non-atomic, but some people look at it as a repeating group. Either way, it's the same thing. We've got a problem. So to get rid of this problem, it's very simple. All I do is add a new row. So that's my original, and here's my new row. So now Dorothy Sayers is on a row by herself, and this Robert Eustace is on a row by himself, and same with these 2 people here. Now I'm perfectly fine. Every column is unique, and each column is atomic in a sense, other than first and last name, but that's easy to fix. But I'm talking about the author itself. And no row repeats. See, here, documents in the case. I might repeat the category, I might repeat the book title, but the author doesn't repeat. So the rows are different. So I've met that. So when you see a repeating group like that, you break it down like this. Okay? So now let's go to a real example of a design. Say a client comes to you and they own a small motel. And this client would like you to create some kind of room reservation system. This booking system is to allow the booking of guests. and the client says, I need this kind of information. I want the guest's name, a contact number, like a phone number. I want their email address. I want the type of room or rooms that they would like. So do they want a king standard, a king suite, a 2-queen standard, a 2-queen suite, etc. Whatever the motel has. They want to know what rooms they book, what their check-in date, what their checkout date is, what the default daily cost of the room was, and then what they were actually charged for the room. So for instance, you might say a king standard suite is $100 a night, but this guy is a really good guest. He comes in a lot, so I give it to him for $90. So the default would be $100, and the actual charge would be $90. Maybe they have a CAA membership or an AAA membership or some kind of membership that they get a discount. Or if they book lots of rooms at the same time, they get a discount. Every reservation should have a unique reservation number, so they should be assigned a reservation number. And when reserving a room, the credit card and the expiry date and the card type should be stored. The total cost for the rooms booked and the number of days stayed they need. So they want to know how many days they stayed, and they want to know how much the invoice the client. So if they do $100 a night and they stayed 5 nights, that's $500. That's the total cost of the rooms. Okay. After talking to the client, we figure out a couple more business rules or constraints or requirements. So for this example, we're going to assume that more than one guest, say a spouse, may use the same phone number when they're booking a room, and they can use the same credit card number when they're booking a room. So if a husband books a room, he gives a phone number and a credit card, and say later on, a month down the road, they want to book their hotel again. The wife calls in, and she can give the same phone number and the same credit card, but they can't give the same email address, okay, for this example. And then to simplify this example, we will assume room rates during a single stay period remain the same. So for instance, the cost that they're paying for the room doesn't fluctuate during the one stay. So in real life, let's say you went to a hotel and you booked in 2 days before New Year's Eve, you might pay $100 a night, but New Year's Eve and New Year's Day, they jack their rate up to $500 a night. This doesn't. This would say you pay $100 a night all the way through your stay, okay? Just to make things a little easier for us. And then for this example, we will not concern ourselves with taxes, okay? So make sure you understand all that. Now this last line here, the total cost for rooms booked and the number of days stayed. Remember that requirement, okay? The customer wants that. Makes sense. They want to know how long the client stays and how much to charge them total, okay? So keep that in mind. So how do I start this process? Well, to start the normalization process, just create a single table with all this information in it. That's it. Start it that way. So you create a table that has a column for the guest name, the contact number, the email, etc. Okay, so let's do that. Remember this last line though, the total cost for rooms booked and the number of days stayed. Here's my table that I created. It has all that information they asked for, except that last line. The total number of days stayed and the total for the stay, the total cost. Those total number of days stayed, I can take the difference between check-in date and the checkout date and calculate the number of days stayed. The total cost for this stay is take the difference between the check-in date and checkout date, that's the number of days, and multiply it by the actual room rate. That's the total for the stay, the total cost for the stay. Those are known as calculated columns. So those values or columns can be determined by other columns, can be calculated using data from the other columns. Those are calculated columns. We don't store calculated columns, or we don't make calculated columns in a database, in a relational database, okay? So I left those out because those can be just calculated based on existing data that's in the tables. So there's a table that contains all the information I would need or the client asks for, okay? So is it in first normal form, you have to ask yourself. So what you have to do is, what I do is this: make up some sample data if you can't see it right now. Are there any repeating groups? Well, we have no problem here that every column is unique. Every column name is unique. But do we have any repeating groups here? Okay. Okay, so let's see. Let's just make up some sample data. Just make up some data and put it in like this. So there's the names of the columns, and I just made up some sample data. You can see here Bob Smith, phone number. He booked room 121, which is a King Standard, check-in date, check-out date, etc. Okay? Look down here, there's a Bob Smith there. Same phone number, same email. So it's obviously the same person. He's booked a different room on a different date. You can see this Jane Doe has booked in on the same date as this Bob Smith above him. Okay, Jane Doe here is jdoe@yahoo.com. There's another Jane Doe here, different phone number, different email. So obviously it's a different Jane Doe. Okay, no problem there. So I'm trying to put data in that accommodates different scenarios. Now let's look at this Mary Brown person though. Mary Brown has her phone number, her email, and notice she has room number 132 and 133. During her stay, she's booking 2 rooms, a King Standard and a 2 Queen Standard. So she's got 2 room numbers. She's got 2 room rates and 2 actual room rates. $99 for the King Standard and $109 for the 2 Queen Standard, but she was charged $89 and $99 respectively. And then her reservation number, her card number, etc. You can see this Bob Smith used the same card on 2 different bookings, 1122 whatever 333 and 111222 333. Okay, so I have some sample data, and right away I can see a problem here with multiple values. Okay, it's not atomic or a repeating group, depending how you want to look at it. This column, and this column. So how do I get rid of that? All I do is make a new column for each of these rooms. Very simple. So let's do that. There I go. Mary Brown. Boom. Took care of that. Now I have the name Bob Smith. Technically, to make this atomic, I should split this up into a first name and last name. I'm not going to do it now. I'll just remember to do it at the end, okay? Just because I have no room on the screen. So I will take care of that way at the end. So now I've split up everything. I have no repeating groups now. Now what you got to do before you say you're finalized in first normal form is find an actual primary key in this table. So what's the primary key? So the biggest, we have no null value, so we don't have a problem with that. But what we got to do is find a key that creates uniqueness. Okay, so what we want to do is, let's look at this. Can the name by itself be a primary key? So in other words, no value can repeat. If the name is the primary key, there's Bob Smith there, but look, there's Bob Smith again. It repeats on a different row. Can't have that with the primary key. If you look at phone number, again, that phone number repeats. The email repeats. Room numbers repeat. Room types repeat. Check-in dates can repeat right there. Checkout dates could repeat right here. Okay. Room rates again repeat, etc., etc., etc. So one single column in this table cannot be a primary key. So the chances are it's a composite primary key. Every table needs a primary key. So what we have to do is look at a combination of columns now to make up a primary key. If you want, at this point, you can pause the video and try to figure it out yourself if you wish, before I do it for you. Okay, now I'm going to do it. I'm going to just jump right to the primary key. If you look at room number and the reservation number combined makes up a good primary key. Okay, reservation number by itself can't, because look here. There's the reservation number repeats here. But if I did the room number and reservation number combined, you'll never get a repeat. This reservation number, I've booked a room. You'll never see that reservation number again. So therefore, no problem. Here I have 2 rooms booked on the same reservation number, but this is room number 132, and this is reservation number 128674. This reservation number is 128674 also, but the room number is different. So that combination will never repeat again. So a good primary key is the room number and the reservation number. So write that down. Primary key is the room number and reservation number. Then what you do is you write down what we call a dependency. And what that means is this. Room number and reservation number can determine all the other columns. So you put an arrow and put all the other columns. This is technically called a desirable dependency. Okay, so what does that mean? It means if I know these 2 values, I can determine the values in any of these columns. So let's pick it. If the room number is 121 and the reservation number is 354678, what's the guest's name? It's Bob Smith. What's their phone number? That. Email, that. The room type, that. Check-in, etc. Let's go down to this one, the Mary Brown one, to get a better feel. If I know the reservation number is 128674 and the room number is 132, that will only appear once, therefore it will pull up 1 row, and it will be Mary Brown and her phone number. King Standard, the check-in date, check-out date. I can determine anything I want on that row, any of those columns, the values, if I know those 2 values. If I know the room number and the reservation number, I can determine any of these other values, because I'll never get a repeat of the combination of these 2. That's what the primary key does. Okay, so now I'm in first normal form. Okay, I've met all the requirements of first normal form. Now I'm going to check, do second normal form. And second normal form says you're in first normal form, which we are, and remove partial dependencies. Partial dependencies only will appear when you have a composite primary key. We have a composite primary key. We have room number and reservation number. So the chances are I have a I will have a partial dependency. So to do that is very simple. You write down room number and reservation number by itself. So that's the primary key in one table. Then you take each part of the composite key, room number, and you write that down in a new table and make that the primary key in the table. You take reservation number, make a new table with that, and you will make the reservation number the primary key in that. And now you ask yourself, what can you determine if you know just the room number? Let's look at that. Again, if you want to pause the video and figure it out yourself, go ahead. Okay. So if I know the room number is 121, can I determine the guest's name? In other words, is it whatever I get has to always have the same result? So 121 is Bob Smith, but if I go down here, 121 returns Jill Johnson. So I'm getting 2 different results. So I cannot determine the guest's name if I know just the room number. What about the phone number? No, I get 2 different phone numbers. What about the email? No, I get 2 different emails. What about the room type? King Standard, King Standard. Okay, so you can see that knowing the room number, I'm always going to have the same room type. Now, if they renovate and change the room types, that's not going to work at this point, but we're not doing that. So room number can determine the room type. If I know the room number, I know the type of room it is. It's a king standard for 121, a king standard for 125, etc. Okay, that's not going to change. Can I determine the check-in date? Well, 121 has this check-in date. This 121 has a different check-in date. So no. Checkout date? No. What about the room rate? Yes. 121 can determine the room rate because it's $99 as long as I never change the room rate. What about the actual room rate? No, because this person paid $89. This person paid the default, it's $99, so you can't determine that. Reservation number changes, card numbers change, etc. So if I know just the room number, I can determine the room type and the room rate. So you write that down. So now I have a new table with 3 columns in it: room number, room type, and room rate. Room number being the primary key of this table. Now look at reservation number all by itself and figure out what you can determine. If you know the reservation number, can you figure out the guest name? Yes. See here? Reservation number repeats here, but look, it's always the same person, Mary Brown, because she booked 2 rooms. So reservation number can determine the guest name. It can determine the phone number and the email. Can it determine the room number? No. But what you'll find is these fields you can ignore now because they're out of this table now. You don't have to look at those. But you can see that it wouldn't determine the room number. Okay, it also would not determine the room rate or even the room type. So we don't have to worry about those. Can you determine the check-in date? Yes. Can you determine the checkout date? Yes. Can you determine the actual room rate? No. Look, same reservation number, but you get 2 different room rates or actual room rates. So no, I can't determine the actual room rate if I know the reservation number. Can I determine the card number? Yes. The card type? Yes. And the card expiry? Yes. So in the reservation number table, put all those columns in it. You notice actual room rate is not in any of these 2 columns or 2 tables. It was in the original, so where does it go? Well, it goes into this table. You can't lose any of these columns. They all have to exist now. So any column that is not part of the partial dependency stays in the original table. So actual room rate stays in this table. These are called the partials. I've removed them now out of this single table and made them into individual tables. So now I'm in second normal form. I'm going to redraw this as real tables now. Okay, right there. Room number, room type, room rate. I have the reservation table, reservation number being the primary key, and all these columns are in it. And then I have the original table with the composite primary key and the leftover column that could not be determined by just these individual columns. So now I have 3 tables. And you'll notice when you go up in normalization, you get more and more tables. So now the third normal form says you're in second normal form, which we are. We've removed our partials. And you have to remove now transitive dependencies. Transitive dependencies say that all the columns must be only dependent on the primary key of the table. So let me show you the first one, the most obvious one. Look here at this card number, card type, and card expiry. If I'm not showing the data again, you can always reverse it to just look at the data again if you can't visualize it. If you know a card number, you would know the card type. So if you gave a card number, looked up the card number in the data, the card type never changes, right? If my card number is 1, 2, 3, 4, 5, 6, and it's a MasterCard, it's always a MasterCard. It also has the same expiry date in this example. That could change in the future, but for this example, I'm leaving it the same. Like obviously, when you renew a card, you get a different expiry, but I think they keep the same card number again. But for this example, I'm going to say the card expiry won't change. Okay, so that's a transitive dependency. So you make a new table with card number is going to be the primary key. That should be underlined. And card type and a card expiry are in that column table. So now, can you see any other transitive dependencies? Again, you can pause the video here and see if you can figure it out on your own. All right, let's continue. Obviously, the name can't determine anything because remember we had two, I think it was Jane Doe's. No, Bob Smith's. We had more than, no, Jane Doe's. We had more than one Jane Doe. They were two different people, so the name won't. And the phone number doesn't because of that business rule I gave you away at the beginning that the same phone number can be used, say, for two different guests, like the husband and wife. But I did say the email had to be unique between them. So the email, if you know the email, you can figure out the guest's name and their phone number. Again, you can look at the data. So now I have a new table with email as the primary key, and it can determine the name and phone number. Are there any other transitive dependencies? Not in this table, but up in this table, room type. If you know the room type, say it's a King Standard, the room rate is always, I don't know what it was, I think it was $99. 2 Queen was always whatever it was, etc. So if you know the room type, you know the room rate. Okay, room type, room rate. These are known as transitive dependencies. I don't need to figure out the card type and card expiry. I don't need the reservation number. I could do it using another column that's not part of the primary key. Okay, those are what transitive means. So these are 3 transitives. So these are 3 new tables. Okay, so we have these 3 tables and these 3 tables now. So let's redraw this and show you what you do though. So here is the original 3. Here's the 3 transitives. Now what you do is this. Let's start with the room type. So you write this table down. Room type, room rate. Make room type the primary key. Up in this original table, what you do is you leave this column, room type, in, and you take out room rate. This column. So now there's the original table, room number. I left in the room type, but I took out the room rate out of this because the room rate has been moved to here. What this is doing, this becomes the foreign key to this table. These 2 tables are related to each other. Now let's do the card number. So there's a new table, card number, card type, card expiry, with card number being the primary key. Therefore, I take out card type and card expiry out of this table. Okay, when the email, there's my email name and phone number. I will take out name and phone number out of this table. So now that table becomes reservation, the email, that's linking this table, the check-in and check-out dates, columns, and the card number, and that connects that table. Okay, so I took out card type and card expiry out of here because it's already up here. I took out name and phone number also, and then this table, nothing happened to it, so I leave it the same. So there's my final design. Now let me redraw this to show you what this looks like in what we call a relationship schema diagram. This has automatically been done and has surprisingly done all the foreign keys, all the relationship types, and guess what? The bridge tables. Let's see. So I've just redrawn it. Here's the room type and room number. Look at this. Room type, and there is the room type there. Remember, the foreign key is always the many side. So I have a 1 to many here. Look at the guests. I have an email to the reservation, 1 to many. Card number to card number, 1 to many. this reservation number up to here, room number into here. The two columns were combined, making a composite primary key. Individually, they're foreign keys. So what does this table look like? Oh, lo and behold, it looks like a bridge table. Two columns, composite primary key. Individually, they're foreign keys. Okay, so a guest makes a reservation. They use a card for that reservation, and they can book many rooms on that reservation. So look at this. Each reservation, or one reservation, can have many rooms on it. Each room can be on many reservations. Remember that room 121 was on multiple different reservations. So that's a many-to-many relationship between these two tables. And how do you get rid of a many-to-many relationship? You put a bridge table in between. What's the minimum number of columns in a bridge table? This column and this column. So two combined make up my primary key. Individually, they're foreign keys. And the actual room rate is the extra column I add, because when I book a room, I can change the rate, right? This is the default rate, but this is what they're actually being charged. This is an interesting one. If you looked at it originally, you might think a card number is associated with a guest. It's not. The card number is actually associated with the reservation. Pretty cool. If you're doing a banking application, the card number would probably be related more to the, what do you call them, a client or a customer of the bank, right? If I want 5 credit cards with the banks, it would be really to the guest probably. But in this case, the card number is actually applied to the reservation, is related to the reservation, not to the guest. But I can still figure out which card number a guest used by going through here. I know the email address, and now I can get the card number. So I know who booked it. Okay, so that's the final design in the normalization. Now, let's put in some sample data. All that sample data I did, let me show it to you in here with the actual data I had. And there you go. That's how it looks. That's how it actually looks stored in the database. So let's analyze it a bit here. So this Mary Brown, remember she had 2 bookings. Here's her reservation number, 128674. I go up here, and I find 128674. Look at that. She booked room 132 and 133. She paid $89 and $99 for the 2 different rooms. What kind of rooms were those? 132, 133. Oh, it's a king standard and a 2 queen standard. What was the default rate for those? King standard was $99 and the 2 queen standard was $109. Let's go back to her. What credit card did she use to book this reservation? Go down here, 888888. She used a Visa, and the expiry date is 9/22. Who actually is this person, Mary Brown? Give me more details about her. Mary Brown. Oh, that's Mary Brown, and here's her phone number. You can have in here her address, like her home address and everything in this table if you want it. Okay, so that's how that works. Now, technically, this design is perfectly valid. It meets all the requirements. I personally don't like this. The reason I don't like it is this. These columns here, they contain actual business data. So these are actually called business data as the primary keys. I don't like using them. I like my primary keys to have nothing to do with the actual data. So what I would do is this. I would, and I don't like having to repeat this king standard and queen standard way over here in the foreign key. That's too much. I like my primary keys just to be numbers, auto-generated type numbers. So I would change this by adding a new column into this table, this table, this table, this table, and this table. This table won't change. other than using a different column value. Okay, so this is what I would do. And let me redraw it with the data. So it would look like this. So notice this one here, the room type isn't going to type in King Standard, King Suite. I use a room type ID now. Okay, so let's find this person. Reservation 128674, which was Mary Brown, number 4, right there. So her reservation ID is a 5. You go up here, 5. There's 2 rooms booked. Room 4 and 5 ID. What is that? Room 4 and 5. Right here is actually room 132 and 133. What type of rooms are they? A 1 and a 3, which is a King Standard, and a 2 Queen Standard. So I like my primary keys to have just be whole numbers or numbers that have no decimal places. Okay, so that's how I like mine. But the previous one, perfectly valid. I would just make this slight change at the final end. And notice what I did was I atomized the column for the guest name at the end here. I put the first name and last name in 2 separate columns. The reason I do that is if you're searching for all people who have the last name of Doe, it's easy to search this column. If they were combined and they said, oh, their name is Jane Doe, type them both in and search, no problem. But if you're looking for a mailing or anything to do with just the last name, how do you figure out the last name? Do you split it with the second word, or is it the third word, or they have a middle initial or whatever? So it's hard to see. So it's always useful to split up that. That's why we want them atomic. Okay, so that's it. That's the final design. That was normalization. Hope you enjoyed that or picked up some pointers. And if you like this video, please click on the like, and please subscribe to the channel. And if you want to see any new videos when they're posted, click on the little bell icon to be notified. Anyways, everyone, have a great day and take care.